All right, so we're gonna continue today with lecture 10, which is going to be about nonlinear signal models. But just to make sure we're all on the same page on the discussion of the theory of critical exponent, I'm gonna review it and include a little bit more detail, because I think last time there was a question that came up about the beta function of QED, and you guys all unanimously gave the wrong answer. So I have to make sure I explain that properly. All right, review of lecture 9. We discussed the theory of critical exponents, statistical field theory. So recall every time you think about this, think of this simple example, a bunch of spins up and down, and you are coarse graining them by spin blocking them into groups and calling this variable S of X, and the low frequency long distance regime, thermodynamic regime at low frequencies, which is the continuum limit. You end up with a continuous field S of X, which in this case ends up being a real scalar field, right? Okay. The partition function of this statistical field theory, Z of beta, in the presence of source beta, external magnetic field, B, sorry, not beta, B. I don't know what, as a path integral over S of X, right? Which is a coarse grain magnetization, local magnetization, e to minus beta H plus integral of B of X, S of X, right? The Helmholtz free energy. So this Z of B is the generator of the thermal correlation functions. Helmholtz free energy, which is minus 1 over beta log ZB, is the generator of the connected correlators, right? And using f of b, we could take derivatives and calculate correlation, well, or ZB, you could calculate correlation functions, in particular the 1-point function, m of x, right? This is the analog of phi classical. This is the 1-point function of a quantum theory, or here in this case, the average 1-point function of a fluctuating finite temperature theory, right? We said that if we have m of x, we could do a Legendre transform and get a Gibbs free energy, which is now a function of the 1-point function, by just adding to the Helmholtz free energy an integral of m of x, b of x. As a thermodynamic theory, the thermodynamic variables are inverse temperature, beta, b of x, external field, and s of x, right? These are magnetization and external field are the thermodynamic variables that, going from Helmholtz free energy and Gibbs free energy, we trade them, right? To trade the functionality of them. The goal would be to calculate S as a function of B, or B as a function of S, right? Okay. Now, what is a phase transition? Actually, what's a phase transition? Phase transition is non-analytic behavior of free energy as a function of the thermodynamic variables, right? Non-analytic, meaning that, for example, the first derivative of thermodynamic, these quantities, thermodynamic quantities, could be discontinuous, in which case we say we have, so it's a non-analytic behavior, but it's not always true. Keeping is non-analyticity in the thermodynamic behavior as a function of beta, right? Once we tune beta, or if there are other couplings, to some critical value T of C, the partition function blows up, right? Log of the partition function will have non-analytic behavior, right? And so do correlation functions. The first order phase transition is, by definition, discontinuity in the first derivative. The characteristic of the first order phase transition is latent heat. people used to call something second order phase transition, where there's a discontinuity in the second derivative, but the modern terminology is continuous phase transition. Anything that's second order or higher order. Right? It's just first derivative is continuous, but some higher order derivative is not. There's no latent heat. And these theories, these phase transitions are the ones that are characterized by universal critical exponents. So this is just an observation. You might have learned about this from StatMech, or theory of critical phenomena. But the physics of this comes from the following fact, that it's understood that in these systems that undergo continuous phase transition, if you calculate the 2-point function, right? Say the connected 2-point function. For example, Sx S0, it's going to fall off exponentially fast, right? And the coefficient of the exponent, because this is dimension full, you have to have a dimension full parameter. That dimension full parameter is called correlation length. To get non-analytic behavior of this type that we're discussing, correlation length will have to blow up at the critical point. So correlation length, which is, hopefully you remember what correlation is, right? The scale at which you see correlations, beyond which you don't see correlations. Correlation length goes to infinity, which means that no matter how large the size of the system is, so sorry, if the correlation length is finite, going deep in the infrared, at some point, you're looking at scales larger than the correlation length, the theory is trivial. So if you want rich physics with all sorts of degrees of freedom that are fluctuating deep in the infrared, you have to have long correlation, right? So this is like, goes hand in hand with that. The theory at this scale is scale invariant because, well, correlation length has gone to infinity. All the other length, there's no other length in the problem. So it has to be scale invariant. The only expressions you could write down will be just dimensional analysis of these guys. Will have to be parallel, right? Now, if the theory is free, massless, or trivial fixed point, trivial scale invariant, this 2-point function is basically decided by the canonical dimension of the field that we write down in the action, right? It's basically decided by the symmetries, transformation. If it's real scalar field, as in the case of the spin model, right? The canonical dimension of a free scalar field in D dimension is D minus 2 over 2. So there are 2 of them, so it's got to be 1 over x to the power of D minus 2. Now, we could have non-trivial fixed points. We could have non-trivial scale invariants, and they're characterized by setups where there is this exponent is not the canonical one, is not the free fixed point one, trivial one. It actually has a shift. That's the anomalous dimension. This is an exponent that is universal, right? It's fixed by the symmetries. And we said that quantum field theory is very powerful when getting these coefficients. There's another universal exponent in the way that the correlation length blows up as you approach the critical temperature. So if you define this little t, which is a dimensionless parameter that characterizes how far you are from the critical point, right? Correlation length as a function of this deviation from criticality scales with a critical exponent nu. There are other quantities that show scaling laws, but the punch, like specific heat, magnetic susceptibility, but the punchline is that in a phase transition is non-analytic behavior in non-analytic behavior of free energy in terms of the thermodynamic variables, right? if this non-elasticity is second order or higher, like is in second order, second derivative is discontinuous or higher derivatives are discontinuous, then this is continuous phase transition, and they are characterized by a set of numbers, just numbers, right? That you will have to evaluate or measure in experiments. They're called critical exponents. And field theory provides potentially a way to, Wilson-Fisher fixed point provides a way to understand this. The fact that these critical dimensions are not all zero, well, actually not, the critical exponent, this anomalous dimension is not zero, is the indication that you're talking about a non-trivial fixed point. If you have massive free fields, what is C? Inverse mass, right? So if you have a trivial fixed point, right? This is mass. This is just inverse mass. Correlation length is inverse mass. So you can totally see why when we say correlation length goes to infinity, all the masses have to be zero, right? That's related to the fact that the theory is dimensional scaling varying. All right. The fact that we see examples of this, examples of such non-trivial fixed points and continuous phase transitions around us, there are many examples, point to the existence of interacting fixed points in the infrared with these critical exponents. Indeed, equal 4 and higher dimensions, we showed that at least real scalar field doesn't have interacting fixed points. But in D less than 4, they could exist. And as an example, we studied Wilson-Fisher fixed point. So I'm just reminding you what the Wilson-Fisher fixed point was. Let's start with the ON model, right? Why ON and not just real scalar fields? Because I want to tell you about the Lagrangian trick. I could do this with n equal 1, and I won't have any punchline. Let's start. Oh, actually, another thing. There's one more reason for that. Actually, yeah. These critical behaviors we're talking about, right, are often associated with some development of some one-point functions, right? Remember, the one-point function is the first derivative, right? So the first derivative is going to be non-zero or something. But at the critical point, you end up with some one-point functions for the system, right? It could be small, but near the critical point, your phi is not necessarily zero. That's why when I start with the Lagrangian density for the ON model, I'm not gonna expand around the trivial. Well, I can expand around the trivial point. So remember that at the end of the day, the punchline is going to be that they're perturbatively close, right? So this is the trivial fixed point, and this is Wilson-Fisher fixed point, right? I can expand around here where the one-point function of field is zero, right? Near here, it could be non-zero, right? That's why in my analysis, I'm just assuming that there is a one-point function. So there is spontaneous symmetry breaking. Phi of A of X is some phi classical, right? Because we have a one-point function, we're going to be working with Gibbs free energy. You recall the distinction between the two was really this one-point function.
We are talking about continuous phase transitions.
Yeah.
So the first derivative is anyways continuous. Like the first derivative is
it's continuous.
So that means phi expectation value of phi is a continuous.
Yes. So it starts from zero at high temperature is zero. At the critical point is zero, but below critical point starts growing. But continuously. We never say it's smooth. It says continuous.
So I'm just trying to have some lines this as spontaneous symmetry. It's like the expectation value we feel is if it's not, you know, at the critical point. then-
Yeah. So, okay, sorry. Deep in the infrared, if you look at the vacuum of this theory, it has spontaneous symmetry.
Um,
Right, sorry, that's what I mean, right? But here, remember that spontaneous symmetry breaking is in the language of quantum field theory, where your beta has become h bar. Right? So in the finite temperature, you're talking about the configuration that minimizes free energy. In the quantum case, you're talking about the vacuum of a Q of T. Also, we can talk about whether, yeah, okay. But the terminology is used in general, like for low enough temperature, large enough beta. All right. So we're going to be calculating, we did calculate the effective action at one loop for this model. It was basically the action for the classical field plus I/2 log of the determinant of the kinetic term plus the mass matrix, right? We said that we're breaking ON to ON minus 1. We're going to end up with still N minus 1 massless fields. Sorry, not massless fields. ON minus 1 symmetry in the remaining pi's. Sigma and pi was how we called them, right? And the corresponding masses for sigma and these pi fields are going to be different. One of them has 3 lambda phi classical squared. The other one has this. The renormalized effective potential is going to have this piece that's just a function of the background classical value plus this. We went through the renormalization of this, or at least I told you how it works. Now, to trust this has been evaluated at one loop, around one loop expansion, right? And to trust this calculation, you want to make sure that mr squared and lambda r are small, right? Now, we went through the Kalin-Simanzik for effective action. If you recall, this is what it was. I did not derive this last term. I left it for you guys to derive it. You plug it in, you expand it in small phi classical, order by order, all the terms should match. And we found the beta function for lambda and the renormalization of the weight functions gammas. In D equal 4, this is what we found. Now, we want to interpret this properly, right? Let's go back and remember what the beta function is. This is the beta function. MdM of lambda is beta lambda. Imagine that at the cutoff scale, everything is lambda. Capital lambda, your coupling is lambda naught. Then I'm going to define the scale m as b lambda, b less than 1. So I'm going to do RG in the sense of integrating out momentum shells. All right, so MdM becomes BdB of lambda is beta lambda. Let's integrate. On the left side, I end up with integral from lambda naught to lambda of d lambda prime over beta lambda prime is minus log of 1 over beta. I write 1 over beta because b was less than 1, and I want to write something log of something larger than 1, so that's positive. So now this clearly is negative. Good. So in the example that we saw here, and the other, and all the other examples we've been looking at, beta lambda starts at order lambda squared or later, right? So there will be beta 2, lambda 2 plus higher orders. So imagine lambda is small, so I can just focus on this term. This equation becomes just this, right? This is the UV coupling. This is the coupling at scale B. And you could solve it to find the following equation. Let's stare at this equation. This is the value of the field coupling at some lower scale m as a function of the UV coupling, how much of integrated down how the difference between the UV and the scale of interest and the value of beta 2. If beta 2 is larger than 0, lambda decays because this gets larger and larger, so this goes down. As you go towards the infrared, lambda decays. What does that mean? What did we call such a term? Irrelevant. Beta equals 0, lambda is unchanged. Beta 2, sorry. Well, beta equals 0. And beta less than 0, lambda grows towards the IR. That's irrelevant. So this was marginal, this is relevant. Now, we said irrelevant terms are bad, right? This is irrelevant in d equal 4 dimensions, right? So in d equal 4 dimensions, O1 model, the fate of O1 model and real scalar fields are the same. There's just no interacting fixed point. That's why we went to 4 minus epsilon dimensions to find the Wilson-Fisher. All right, but what is, when we say the fate of, there exists none, let's say a few more words, because I'm going to say in a second that QED is like that. We calculate the beta function of QED, and it turned out to be beta 2 is actually positive. So what does this mean? There is something really sick about it. Let's invert this relation and write lambda naught, which was lambda at the UV cutoff, in terms of the lambda observed at energy scale m. So in QED or this model, let's say at some scale m, I observe something. I know in the UV it must have been larger. But how large? If you invert this relation, this looks like when there's a minus sign here and beta 2 is positive, it means that at some value of lambda, finite value of UV energy, the coupling must have been infinite. Right? How do you calculate that? That's a scale. We could just find the pole of this. It's exponentially large. Of course, you cannot trust this calculation at that point. This was a one loop calculation, right? But the one loop calculation gives you something super sick, right? This is called a Landau pole. Do you hear the word Landau pole? It's referring to the fact that you have a theory that had an irrelevant coupling, right? You measure the value at this scale, but you know that not only was relevant, but also you know that at large enough energies, your naive one loop analysis says it must have been infinite. That's called Landau pole. All right, so let's just put together everything we know about these examples of QFT we've worked out so far. Lambda phi 4 and d equal 4. No interacting IR theory. Here's the beta function. It's positive, relevant. QED and d equal 4. This is beta of e cubed over 12 pi squared. We calculated this. Well, we often write the coupling in terms of the alpha parameter, e squared over 4 pi, which was the coefficient of the potential, electric potential, right? If you write it in terms of this, beta of alpha is 2 alpha squared over 3 pi. So a second order G2 term, beta 2 is positive, irrelevant, and it has a Landau pole, right? So QED in 4 dimensions is pretty bad. What does that mean? How is it that we're still calculating QED diagrams using QED to predict things?
Is it because in our range energy scales where things go bad?
Well, it's an effective field theory. As an effective field theory is fine, but Landau pole tells you that at scales way less than Landau pole, there should be new physics. And we know that QED is not the end of the world, right? There is more to physics of standard model than QED. There are more massive particles that are coupled to the photon or QED. The ON model in d equal 4 was also positive. So it seems like So far, we've found no interacting theories in D equal 4. Are there any? In the 60s, late 60s, every example of quantum field theory in D equal 4 that people had calculated had positive beta functions. People were giving up on quantum field theory as a theory that describes fundamental interactions in fundamental physics. It still works for predicting, calculating critical exponents and all, but as a theory deep in the UV, right? People were upset by the very fact, like, so it's so obvious for us that quantum field theory describes nature. But in late 60s, people were just giving up at QFT. The only example that was left that people hadn't calculated the beta function for was non-abelian gauge theory, QCD in particular. At the time, people didn't know QCD was the right description, right? There was a zoo of these particles that people were discovering in collider physics, and QCD was one of the contenders. Well, a theory that we had. There was a heroic calculation of the beta function in QCD. Two groups of people did it. I think Pulitzer, who got it right? Frank Wilczek did it. He found the wrong sign. He told his supervisor David Gross was talking to David Pulitzer's supervisor. He said that David Gross told the other guy, I don't remember, that, oh, my student calculated this and it's negative. But then the other guy says, my student, who was Pulitzer, calculated this and it was positive. So they go and compare notes, and it turns out that it was actually, well, sorry. David Gross got it positive, Pulitzer got it right, minus, and they compared notes, and turns out that it's actually negative. So it considered it was the very first example of a well-defined theory in 4 dimensions, QCD, right? There was a Nobel Prize given for this calculation. Good. We're going to come back to that once we go through non-abelian gauge theory in the next section. But how about D less than 4? Yeah.
I'm a bit confused. Didn't he mention earlier that QED is renormalizable?
Yes.
But
Naive dimension counting, you're normalizing. Right? The proper analysis is calculate the beta functions. That's the proper analysis. We calculate this as one loop, and it had the wrong sign. Of course, if you start with something that was like really terribly relevant, there's not much to check. It's going to come out wrong, right?
if we include higher order loop corrections, can the sign flip or does it never usually happen?
No, it's a perturbative expansion, right? If it starts, yeah, well, there has to be non-perturbative physics. Something good should go crazy. So again, in the vicinity of the point you're calculating, nothing is going to save us because we're trusting perturbation theory, which means the perturbation theory, if we're trusting it, means the second order term is always smaller, it's larger than the third order term. So by assumption, this is true, but non-perturbatively, it's possible that something is going on, right? So how about D less than 4 dimensions? We discussed the Wilson-Fisher fixed point. This is in D minus epsilon dimension, right? And here's the beta function you find. This is the answer in 4 dimensions, and this is the contribution minus. I want to point out that notice that minus, well, actually, I'm not going to comment on this today. Okay, but if for your interest, epsilon is the epsilon term that's negative. Epsilon is positive. 4 minus epsilon. Epsilon is positive, but the coefficient of the epsilon term is negative. That's what I'm saying. All right, so which means that there's a Wilson-Fisher fixed point at this value, 8 pi squared epsilon over n plus 8. We could arrange for this perturbation theory to be reliable by picking small epsilon, or taking epsilon to be equal 1 in 3 space-time dimensions, but taking n to be large. So Wilson-Fisher fixed point describes a genuine interacting fixed point in D equal 4 at large n, which is reachable in perturbation. There are We need more examples of interact, any questions, sorry, any questions?
One quick question. How does this entire analysis change if I consider a complex scale instead of a scale?
So you could think of the complex scalar field as a vector field model as well, right? Where the symmetry is complex. U1, right? So it's an analysis you could do, and I invite you guys to do. I'll leave it at that. It'll probably be a homework problem. All right. But you sort of know the answer based on the bedtime story of QCD I just told. So far in D larger or equal to 4 dimensions, we've not found any interacting QFTs, but we seem to have, as our analysis of renormalization group analysis suggested that there should be a zoo of D equal 2-dimensional interacting QFTs, right? Because D equal 2 was a setup where everything was marginal, right? For a real scalar field, the conformal dimension of phi was the canonical dimension of phi was scaling dimension of phi was 0, which meant that phi to the power of n is marginal, right? So you could just put whatever you want. It seems like potentially these are all pointing at interesting interacting quantum field theories. So now the question is, can we use 2-dimensional quantum field theory to describe fundamental physics? Remember the mentality, right? The mentality was like, oh, well, let's say we haven't seen QCD yet, but like most of these models that we're trying to build up in 4 dimensions were turning out to be true, right? We want something want to build something for the fundamental theory, for fundamental theory of particle physics, which is going to be 4-dimensional, right? Can we recycle all this technology we've developed? This is the way I'm pitching it. Of course, the story of this is older. So now today we're going to talk about one of those ideas, nonlinear sigma model. It's a very simple way to explain it. Remember, so far we've been thinking of space of fields and space-time. We talked about the fiber bundle structure. M is the space-time, and at each point in space-time, the field could take values as a point in some internal manifold X that we're going to call target space. So formally, a field is a map from space-time to the target space. Right? Now there is a connection, blah, 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 but let's not worry about gauge theories or any of that. Right? Formally, for global symmetries, if I have global symmetries, this is what the story is. So phi of x mu, the value of this field at a point in space-time, is phi of a of x, where x mu, where this a is the index for, like this phi a is our coordinates for this internal target space manifold. We imposed locality in M, right? Space-time, we were talking about actions that are local in space-time. But formally, what if we change the roles? What if we interpret X as a space-time and call this M, could treat this M as some sort of auxiliary space? Right? So this is the idea of nonlinear sigma model. Now, how could this be helpful? Well, the problem was that there was a bound on the dimensionality of this M. We could take this like auxiliary space M of the field theory with respect to which the Lagrangian or the action is local, Lagrangian is local, to be 2-dimensional or 1-dimensional, 3-dimensional, right? And keep our space-time still whatever dimensional we want.
What is the nature of this mapping? I mean, is it one-to-one?
This what?
What is the nature of this mapping? Is it one-to-one?
Is it 1-to-1? definitely not one-to-one, but it's a function, functional. To every point on the roll line, or sorry, on every point in M, you associate a point on X. Right? For example, the field could be 0 everywhere. That's clearly not one-to-one. Right?
Yes.
Classical field theory. Now, all right, so this is the main idea. And I'm gonna do this in a funny way. Well, actually, in the interest of time, I'm not gonna do 0 plus 1, 0 plus 0 dimensional QFT. Because now notice that now when I say 0 plus 1, 0 plus 2, 0 plus 0, it's about the dimensionality of this auxiliary space. Who cares about that? That's just something for me, right? I'm gonna think of my space-time as being X. Right? It's an example for you guys to think about what 0 plus 0 QFT is and nonlinear sigma model is. I'm going to discuss 0 plus 1. Okay? It's nothing but a relativistic free particle. All right. In 0 plus 1, M is a line, time, and I'm going to call that the world line, not surprisingly. Field is a map from R, a point on the world line, say, I don't know, some that I'm going to parameterize by some t, to X is a point in space-time. So phi of t is just X mu of t, where the particle is at time t. Right? So this is my field. This becomes quantum mechanics, particle quantum mechanics. All right, so this is my t, this is my X. I'm going to view X as space-time, and now the location of the value of the field becomes just a curve in space-time. In the target space, I could pick a metric, right? Flat space metric. I could make the theory, try to make the theory relativistic in the target space. We'll work towards that. Remember that, notice that relativity, or sorry, symmetries of the target space is something that we have to implement into the action. ON model had the ON symmetry in the internal directions. Now, here, what we want is something that those internal directions are becoming space-time symmetries, right? So we want to see how that comes out. Relativity, right? Relativistic, if you put something like flat metric, Minkowski's metric, it will have to come out. All right, so what is a Schrodinger action? What Schrodinger state? A Schrodinger state is just at time t, you have X mu. This is at some time t, you have a field configuration phi. What's a canonical conjugate variable to the field is just the momentum and the space-time. It's delta of phi, which is what we call P in quantum mechanics, right? All right, so it's clear what Hamiltonian density I'm going to write down. I'm going to write down minus half h mu nu pi nu yh eta mu nu, because I know that if I put this, I'm going to get some relativistic answer out. Plus half m squared. I invite you guys to think about why I put half m squared here. First of all, why m squared? Yes, but dimensional, well, it's mass squared. Why mass squared? This is Hamiltonian density, right? Okay, and my R is now time. It's you gotta think a little bit about how these terms work, but this is the only thing that's natural. All right, so here's my line. I'm gonna okay, so let's try to derive the path integral formalism for this thing, right? We're gonna do step by step everything we did for quantum field theory. I could have done this in like beginning of last semester. In retrospect, next time I teach QFT, I will. So we're after the amplitude xi mu si xf mu sf. Right? How do we calculate this? Whoops. This is x mu j. No, there's no mu here. Whoops. We're gonna insert a whole set of we're gonna split this into many pieces. I think I'm missing terms here. Whoops. No, that's fine. That's fine. So on each of these points, I'm gonna put a resolution of identity. That's what I'm doing, right? Then I'm gonna write down this time evolved Schrodinger state as the time not evolved and bring out the time evolution explicitly in terms of the Hamiltonian density, right? The rest is just the standard tricks we did to do the path integral. There's the Hamiltonian density. I take this out. I get the overlap of this guy. It's just a phase. Now, this is my internal direction, R, right? That I'm going to parameterize. Notice that the parameterization of this is just very arbitrary. Just how I want to parameterize this internal space. I'm not going to pick them to be equal distance. I'm going to just pick them to be EJ some delta S. So here's S1, S2, S3. They're not equal. They're not evenly spaced. And EJ is a local reparameterization. As n goes to infinity, different choices of these parameterization S's or E's correspond to mapping T to some T prime of T. All that matters at the moment is order preserving. Later points in time should remain later in time. But I can change the time differences. That's a redundancy of the description. It's like a gauge mode. All right, so here it is. I take the continuum limit, I end up with the following path integral. Path integral over d of E of S, which is now there are two sets of fields that live on this world line. One is the x mu of S. The other one is E of S, which is reparameterization. There's a path integral over both of them with the appropriate, it's no longer phi, x. Initial conditions, but the action that you have inside the path integral has the following form. Minus E minus 1 over E of S, eta mu x dot nu minus half this guy. This is the action. There are a whole bunch of things. Are there any questions? Maybe I should pause here. So what did I do? I said that in nonlinear sigma model, we do the same calculation we would be doing in quantum field theory, just this time interpreting the target space, internal direction of the space time. I'm gonna pick my the domain of the work. Sorry, my old space time, right? M to be some lower dimensional thing, right? And reparameterization. In this case, I took it to be 0 plus 1 dimensional, and the reparameterization of those are not very physical. So I ended up with E of S, degree of freedom field that keeps track of those reparameterization, and X mu of S, which is my dynamical field. Now, this is the classical action. Let's just analyze this classically. There's some very interesting stuff about it. First of all, this, to be honest, I don't know about you guys, but every time I see this derivation, I've seen this many times, every time E of S is confusing. So let's calculate, if it's a field, let's calculate its, derive its equations of motion using variational principle. So what's the equation of motion? This is what you find. You find that eta mu of pi mu pi nu is m squared eta s squared. This is a constraint. This is not a dynamical field. if you evaluate the Hamiltonian density on the shell, on the solution to this equation of motion, the Hamiltonian density is 0. This is a sign of a diffeomorphism invariant theory. This happens in gravity in higher dimensions as well. It's a constraint. It's not a dynamical field. In the saddle point approximation for E of S, you could evaluate this, you could approximate this path integral by the value of this on the saddle point for E of S. So you end up with the following path integral. Now, plugging in the on-shell thing inside this gives you this very, very familiar action. It's a relativistic point particle, free point particle, which is quantum mechanics, right? So 0 plus 1 dimensional nonlinear sigma model just became relativistic point particle, quantization relativistic point particle, a la path integrals are fine. If you recall, when we said quantum field theory in 0 plus 1 dimension is quantum mechanics, if you were confused about that statement, here's another way to think about it. Any questions? The action is the proper length of the embedded curve in target space. Remember that this is first quantized relativistic free particle from the point of view of quantum mechanics. But from the point of view of the non-linear sigma model, this is like a quantum, there's a Fock space, so quantum field theory. Now, what happens if I go to, if I consider two-dimensional nonlinear sigma models? What is my M now? It's two-dimensional. Previously it was world line. Now we're going to call it world sheet. Right? So fields are maps from the world sheet to the space-time. That's, by the way, string theory. In case you're wondering. Nonlinear sigma model in D equal 2 is very useful. What's the main use we've argued for up to here? Sorry? Yeah, it's a candidate for building interacting quantum field theories in higher dimensions, hopefully. Well, quantum field theories, right? So we're gonna be after calculating the beta function. But before talking about what I mean by, well, actually, let's say a little bit more about this. So here's your world sheet, and under your field, at every point on the world sheet, you have a field that takes value in space-time. There's a metric in space-time, Gij, which is like a metric in the internal manifold of the fields. Right? That metric is a function of the field value of the field, right? This is the tangent space metric, sometimes called the sigma model metric. This is nice, as I said, because in 2 dimensions, the scaling dimension of phi is 0. So at least naively, the Lagrangian is generalizable for any metric Gij. Yeah.
I'm a bit lost here. We were claiming that my target space is now n, which is a world sheet, right?
My target space is space-time.
Okay.
Right? This is space-time. My world sheet is, yeah.
Okay.
So before talking about space-time, let's try to solve a simpler model. This is a model where my internal manifold is just Sn minus 1. This n minus 1 sphere, right? This is really an old example that you knew. This is like the ON model, except that this SO well, not O, it's still ON model, right? But where I allow for this funky metric, this is the metric for on the n-1 sphere. Right? So to write down the action for this theory, remember that I said when I want to put in the metric or the symmetries of space-time, well, internal direction, I have to put it by hand. Previously, I was just writing del mu phi a, del mu phi a, right? To implement ON symmetry. Here, I'm going to do the same thing, but I'm going to input a coupling from the point of view of the world sheet, a metric from the point of view of the nonlinear signal model.
Sorry, can you repeat that?
So Gij of phi, from the point of view of the two-dimensional quantum field theory, it's a field-dependent coupling. So you take Gij and expand it in powers of phi, you're going to get all sorts of interaction terms, right? Various couplings. But it's a generating method for some crazy interaction, right? Notice that this is, when I expand this, it means that I was sitting at, say, phi equals 0, a point internally, right? And I'm just expanding in the vicinity, in the tangent space of this on the field manifold. That's expansion, right? But what it is from the point of view of the target space, it's just a metric. It's just a metric that's nearly flat, or we're going to consider it in the vicinity of the flat metric. Because we're going to do perturbation theory. We're going to do perturbation theory. That's why my field phi is always small, right? So I can linearize this, roughly speaking. But there's a hope that because of the symmetry, I have some full control of this insane list of interactions. So far, remember that we said that under our G flow, all sorts of interaction terms are generated unless symmetry bends orbits. Right? Here is a way for me, and it was kind of ad hoc what terms I added. Right? Here, there's a way for me to write down a non-perturbative some interaction that includes all the higher order terms. I'm going to say in a second. Right? And hope that because there's a symmetry, everything under RG behaves nicely. We'll see that that's literally what happens. There's a lot of beautiful structure and nonlinear signal model. All right, I'm going to take the example. I'm not going to do string theory where X is space-time. I'm going to take X to be a Euclidean manifold, which is n-1 sphere. What is n-1 sphere? It's just pick these guys, fields, to be NAs, and I'm going to add this constraint that the NA sum up to 1. Is that good? Why 1? Is this kosher? Because the field phi is dimensional less than 2 dimensions. So that's a meaningful statement. Right? If my field had a dimension, then I had to introduce a scale to define such a. Right. Good? All right. So the ON symmetry tells me that I can write it this way. Del mu of n squared, 1 over 2g squared. Right? And luckily g is here dimensionless. This is not a free theory. The interactions, it looks like a free theory, except that I have these interactions coming from the constraint that n squareds have to be 1. I can put this constraint inside the path integral, right? And there is this beautiful Lagrange multiplier trick to write down the Dirac delta function as just its Fourier transform, right? This is this Fourier transform with a functional Fourier transform. This way, I think of this as a term in the Lagrangian. Remember when I had the E of S and I said it's a constraint, what the form of it was? I had 2 terms. One of them didn't have any of E of S. Well, I could eat one of the E of S's. And the other one had E of S squared. Has the same flavor. Now we're going to try to solve for the constraint. So we're gonna take the field Ni, pi 1 to pi n minus 1, and this sigma is this as an operator. This is an operator equation I have to include. Sigma is not a brand new field, it's just this combination of fields. So with this plugged back into the action, this is the form I obtained for my nonlinear sigma model. Now it's clear why it's called nonlinear sigma model. This action linearly realizes ON. ON minus 1, sorry. So far when I was talking about the ON model, I was realizing it linearly. But actually the symmetry of this is ON. It's larger than ON minus 1. And to see it, you have to write it in the form of there's a metric that's associated with the SN minus 1 and minus 1 sphere. The extra bit is realized non-linearly. This term and this term, the relative terms are essential to lift ON minus 1 to ON. If I didn't have this term, I would have ON minus 1 realized linearly. This nonlinear term ensures that there's a larger symmetry. That's why it's called nonlinear sigma model. This is the metric on Sn minus 1. That's ON symmetric. Okay. I said all of this. All right, good. So let's take this action. This kind of term we've never dealt with up until now, right? Up until now, we're putting terms in our Lagrangians that were in power series of 5 or derivatives. Here I've put 1 over 1 minus pi squared. That has a Taylor expansion, but the symmetry required that for, right? So if I Taylor expand it, I'm going to get these interaction terms. There's an infinite number of them. Here's the catch. And previously, when we didn't have a symmetry principle, we're adding these terms or term by term, and we had to introduce a counter term for each term, right? Each of them was a different coupling. Here, there was a symmetry principle that gave us, in one shot, an infinite series of corrections, but there's only one coupling that needs to be renormalized, right? So there's only this G. That's the only coupling, and we're going to try to renormalize this, adding only one counter term for this. It should work. We'll see. We'll see if it works. Is the principle clear? Maybe I should pause for a second.
Just lost it. What is the symmetric experiment like you said?
ON,
Okay. Thank you.
right? What is linearly realized is ON minus 1. The ON minus, if I only had ON minus 1, this term is an interaction term. Oops, I could have given a different coupling here. It would have been ON minus 1 still. I could have added higher terms, could have still been ON minus 1. But the fact that it's ON tells me that this is 1, the next term is something fixed, and the next term is something fixed, because they all come from this expansion. It comes from the metric of the Sn minus 1. All right, so let's do Callan-Semantic. We're gonna I'm gonna do Renault perturbation theory, all of that, but in the interest of time, I'm just gonna go very quickly. So Callan-Semantic for the endpoint functions of sigma and pi, but I already told you that sigma is just square root of 1 minus pi squared, so blah blah blah. Here's the Callan-Semantic. We want to compute the beta function and gamma function, and here are the answers. In advance, I'm telling you. In case you fall asleep, g squared over 4 pi n minus 1 is the gamma of g. Beta function comes out to be minus g cubed over 4 pi n minus 2. Negative. Means good for n larger than 3. Right? Okay, so let's work it out. Let's start with the 1-point function of sigma 0. Why sigma 0? Think about what. All right. Sigma X. How do I know that what's the relation between the two? It's about translation invariance in M. Right? That's by translation invariance in M, I can always bring it to 0. By On minus 1, pi I of 0 is 0. Sigma of 0 at one loop takes this correction at one loop. Is pi of 0 squared. This is the Feynman diagram for it. Half is the symmetry of the Feynman diagram. All right, so let's calculate this. The propagator, the free propagator for pi I is ig squared over pi squared p squared delta ij. So this term, this loop thing, is ig n minus 1, because there are n minus 1 decoupled such things that run. Integral of t2k is two-dimensional, 1 over k squared, because there's pi I pi I. Good. Now, this integral is horribly divergent, IR and UV. So let's not worry much about how to deal with the divergences. Let's where our effective field theory at, because we only care about beta function, and say, I'm just gonna do Wilsonian energy from scale M to B minus M. BM, sorry, a little smaller. That means that the 1-point function of sigma at scale M and the 1-point function of sigma at scale BM are related in the following way. They're related by shift minus g squared n minus 1 over 8 pi log of ln of 1 over b. Why am I doing this, by the way? What do I want to read off from this? When I plug this in Kalin-Simanzek, what am I after? Gamma of g. Right? I know in advance that the beta functions are going to come out at order g cubed. If you don't know in advance, you calculate it and you see it's g cubed, so you can drop it at this level. This is at the lowest order what the Kalin-Simanzek equation looks like. You take these derivatives, these are BDB, hopefully you recall that, right? And gamma function comes out as g squared over 4 pi times n minus 1. If I want to calculate the beta function, I consider the 2-point function at one loop for the pi fields. So here's the standard propagator, and here's the one loop correction. This is this propagator, and this is the self energy. Hopefully recall that, right? These should be by now familiar. So we have to calculate this vertex in Feynman diagrams. The vertex is due to this interaction. We haven't dealt with this interaction before, but it's pretty damn easy. Pi dot del mu pi squared. This is the interaction. So I, j, k, l, pi 1, pi 2, pi 3, pi 4. This is what the Feynman diagram is. These are hopefully clear what they are, right? Are these clear? What's the origin of these? Derivatives. Right? When you Fourier transform this, you're gonna have a Dirac delta function that relates the 4 momenta that come in, every pair to the other pair. So there are 3 different pairings. Here are the 3 different pairings. This del mu will bring down one of the momenta. There are 2 pairings of them. Here's the dot product. That's pretty straightforward to calculate it. It's just a Fourier transform. All right, so what we were after was calculating this guy. So let's calculate it. It's delta KL because it's obvious. 1 over 2 is the symmetry. There's an integral over 2k, 1 over k squared, 2p squared plus 2k squared. Now, this is awfully divergent. It's so badly divergent that we're in trouble. The divergence is not consistent with ON symmetry. Why? What is the meaning of this divergence?
That will miss something.
No, what is this divergence? What's the interpretation of this divergence? It's a mass term. It's a mass term for the pi field. Is there a symmetry principle that forbids that? That. What symmetry I have in my system? ON, yes. ON forbids that. It's for you guys to figure out why ON forbids that term. It's late in the evening, I understand.
It's just that there's only a minus one of them.
There's only minus one of them.
No, and minus one.
Well, it's just that. Well, okay, you look at it. Now, if in your Feynman diagrams you ended up with a term that was not allowed by symmetries, we had this situation before. What was it? Gauge theory, right? What was the deal over there? We said that we're using a regularization that was not kosher, right? Here's something else is going on. Here's something else is going on. There is actually a term that we've been sloppy about, and it will come up if you're careful, and we'll cancel this. That term is called contact. To see where it comes from, here's the argument. This is the path integral over the field Ni. This is the action for the field Ni. And here is the constraint. I said you exponentiate this guy, but I lied a little bit. I was too quick. This Dirac delta function is not a constraint on the value of the field N. It's a constraint on the value of the field N squared. Right? So this is your constraint. What I did was that I plugged in the value of sigma as square root of 1 minus pi squared. Right? Whereas this is the condition that I should be dealing with. And if I write the Dirac delta function, it ends up being this. So there is this extra factor that I have to deal with. So let's deal with it. Bring this out. This is e to a power of minus sum over x log of square root of 1 minus pi squared. I'm going to try to view it as a term in the action that I was sloppy about. In the continuum limit, this turns into integral of d2 of x, ln of this term, two-dimensional Dirac delta function 0. This is called a contact term. So I encourage you guys to go through this 2 lines of algebra very slowly to see where this Dirac delta function comes from. It's called a contact term because of the Dirac delta function. What's the interpretation of it? If I were to draw Feynman diagrams, well, let's take this guy and expand it. Right? It's doing to the first order, it's going to be just pi squared. Right? Ln of square root of 1 minus x squared is just going to end up being like pi squared up to coefficient. Actually, no coefficient. No, yeah, coefficient, half. This is a 2-point function. This gives you a 2-point vertex with coupling, which is a Dirac delta function. Delta 2 of 0. This guy will take care of that forbidden divergence. If we were careful from the start, we would have never found it. We would have never found that forbidden divergence. All right, you just plug this, the contribution. Remember that what we're calculating is this plus 1 loop plus that 2-point coming with a vertex we just discovered. You have to add up the contributions. Here are the, so there was this was the correction to the 2-point function, right? There's this integral that was horribly IR and UV divergent. No, sorry. this was the integral with the forbidden divergence. Now I put this next to it. This grows like lambda squared in Fourier space. Hopefully that's clear why. And that lambda squared cancels this lambda squared coming from here, right? Coming from k squared over k squared to give us the remainder term, which is p squared 2 pi over ln of m. This is the 2-point function as a function of scale. So Kalin-Simanzik means take these derivatives, you solve at this order, you find the beta function minus g cubed n minus 2 over 4 pi. For n larger than 2, beta function comes out as negative. So this is relevant. So it's IR safe. Such theories are called asymptotically free because deep in the UV, the theory is free. Asymptotically at high energy, they are trivial. Right? So here's an example of a two-dimensional quantum field theory, right? That is interacting. It's fully meaningful, it's asymptotically free, and it includes an infinite number of terms in this action. It's realizes some nonlinear symmetry. Some symmetry, internal symmetry nonlinear. All right, any questions? I think this is the end of it. Yeah. No? We're good? All right. Thank you, guys.